There is a rectangular coil made up of a conducting material placed inside a magnetic field. Magnetic field is horizontal. North is on the left side, south is on the right side. So magnetic field is from north to south. Coil has two sides. Let's name them for the simplicity. According to the screen, it can be left side and right side. Left side is going up with respect to the magnetic field. The right side is going down because this coil is rotating actually. So when this coil rotates, the side will cut magnetic field lines in the opposite way. The left side will be moving upward with respect to the magnetic field, and the right side will be moving down. There will be two opposite currents produced. In the left side, there will be current produced into the screen, and the right side, there will be current produced out of the screen. So at A and B terminal, because A terminal is connected to the right side and B terminal is connected to the left side of the coil. So at the moment, A terminal will act as a negative terminal and B terminal will act as a positive terminal. But the story will not stay like that forever. In a short while, things will interchange. This coil, because it is moving, there will be a time when this coil will become exactly vertical. Look at the images on the right hand side. They are showing how the coil will be moving. Right now, it is the top position. Look at these images. These images are telling you the side view of the coil as seen from the observer looking at the coil from the side AB. Look at the split ring commutator side. So somebody is looking it from here. So he sees that the left side is going up, right side of the coil is going down. So at A, there will be maximum EMF because magnetic field lines will be cut at a very high rate. After some time, B situation is there. The same coil is moving, but the magnetic field lines are not cut as much as they were cut in situation A. And in situation C, the coil will be both ends of the coil, the top and the bottom, or the right and the left. They both will be moving parallel to the magnetic field line, so no EMF will be produced in this situation. I made this diagram to save time. I made it before class. So look at the first option. The left side is the North Pole, right side is the South Pole, B side is going up, A side is going down. So there will be current outward at A, inward at B. So this is the beginning of time, T equal to 0. After 1/8 of a time period, you can see the second image. Now, although the B is cutting magnetic field line the same way and A is cutting the same way, A is moving downward with respect to the magnetic field, B is moving upward with respect to the magnetic field. So currents will be the same. At B, the current will be going in, at A, current will be coming out, but the value of the current has reduced. Magnitude of the EMF has reduced because now conductor is not cutting magnetic field line perpendicularly. So not the same amount of change of magnetic flux is there. The third option, B is moving towards right, A is moving towards left. And don't forget, magnetic field is from left to right as well. So in this case, conductors are moving parallel to the magnetic field. So no change in magnetic flux. So in this case, there should be no EMF induced at all. Excuse me. Now things have changed for A and B because the coil is continuously moving. Now B side is going down with respect to the magnetic field and A side is now going up. So at A, the current will be going away into the board, and at B, the current will be coming out. So A terminal will be acting as a positive terminal now, and B terminal will start acting as a negative terminal. So half of the time period, T equals to 1/2T, as I hope you can see on the top of the image. A is moving up, B is moving down. So in this case, because again, the motion of the conductor will be perpendicular to the magnetic field. So again, you can see there is positive potential at A, which is maximum, and there is negative potential at B, which is maximum as well. Maximum negative and maximum positive. Now, at 5/8 of time period, like 1/8 after half, you can see A is now moving as B was moving in the second image. A is still moving up. A will still be positive, but it will not be as positive as it was in the previous diagram. Why? Because in this case, A is not cutting as many magnetic field lines as it was cutting in the previous image. So a lesser positive EMF at A, a lesser negative EMF at B. I hope you have seen this diagram before, but in that diagram, A was moving towards left and B was moving towards right, but now A is moving towards right and B is moving towards left. But because the conductors are moving parallel to the magnetic field lines, no cutting, no change of magnetic flux, hence you can see terminal A has zero EMF, terminal B also has zero EMF.
Excuse me, sir.
Yep.
Sir, every time they rotate, the duration of is getting reduced. The time is getting reduced.
No. If it is moving at a constant speed, this is the coil is moving at a constant speed. This is the generator's coil, and it can be moved using an engine, or it can be moved manually. It can be moved by the speed of air in a windmill. Or if I've seen old movies, there we use a guinea pig who's running inside a circular drum, and that is also used to produce this kind of effect. Okay, it is used to move a coil in a magnetic field to produce EMF.
So what you said just now, like when A is at upward, then you said there is very less in magnetic field, magnetic line.
No, it is cutting less magnetic field lines, because
Yes.
I hope you're talking about this image.
Yes, sir.
3/40. Are you talking about 3/40 image?
No, sir. 5/8.
Oh, 5/8. A is still cutting magnetic field lines, but not as many as it was cutting when it was 1/2T.
Comparing to the second image. Comparing to the second image.
Oh, comparing to the second image, yes. It will be like if the angle is same, A will have the exact same electric potential, but it will be in the opposite direction. Hello?
Yes, sir.
So 1/8T and 5/8T, A and B will have exact same electric potential, but their signs have changed.
Is it the number of times?
Number of times of what?
Sir, I could not understand the 5/T or what.
Oh, that like the coil turns in one time, like one complete turn of a coil is one rotation. Time to produce one revolution is called one time period.
Okay.
Okay, this is like there are 9 diagrams over here. These 9 diagrams are completing one revolution. Look at this last diagram. T equals to capital T. It means one time period. After one time period, we have the same situation as it was in the first diagram. Listen, do you see this motor?
Yes.
So the coil is moving. Coil completes its revolution again and again because this coil is continuously moving. So in every one revolution, all this is happening. This is the story of the one revolution explained in 9 equal episodes. So now we make the graph of electric potential develop on terminal B. At t equal to 0, we can see there is maximum potential at B. At t equals to 1 by 8, there is positive potential, but it has reduced. At t equals to 1 by 4, the electric potential at terminal B has become 0. At 3 by 8, it is negative. At 1 by 2t, it is negative maximum. Then it is negative, but the magnitude is decreasing. At 3 by 4t, the magnitude of the voltage or EMF becomes 0. And then it again increases. And this is happening again and again. So this is how alternating current is produced. When we move a coil in a generator, it produces alternating current. Okay. Now, if we make this coil move again and again, if coil keeps on rotating again and again, this kind of continuous variation of voltage and current should be observed. If in across the terminal A and B, I hope you remember the diagram on the previous screen. A and B, if you remember, if this is the graph for voltage in volts, this is maximum voltage. Let's call it V naught. This will be minus V naught. This is where one revolution is complete. So this will be one time period. This will be two time period. This will be three time period. This is time in second. So this is the graph for voltage. This is the graph for current. The values will be different, but the shape of the graph is same. This will be I naught maximum current. This will be minus I naught. Let me connect these waves. This wave-like structure is produced because I hope you remember the EMF was not constant. This is alternating EMF. It is changing direction. It is also changing magnitude. So if the coil this was one revolution. If the coil keeps on moving again and again and again and again, so we should be getting these waves again and again and again and again. And this is how we should end up with this graph. This is called alternating current. Okay, now what is V naught? V naught is peak positive voltage minus V naught is peak negative voltage. I naught, let's say plus minus I naught, is peak current. Peak means maximum current. How can we find average current? But the problem is if we find average for something which is equally positive and negative, the problem is that the average is supposed to become zero, because if there is something which becomes positive and then equal negative and then equal positive and then equal negative, the problem will be when you will find average, you will see that everything will cancel out one another and you will end up with nothing. So here's a technique. If we in maths, if we have a data that is positive and negative both, and we have a if we assume that when we find average, they all will cancel one another, and we will not be, or some of them will cancel one another, and we will never be able to see their actual average. So what we do is we use root mean square technique. So this name is opposite. Opposite means step one, square. Step two, find mean. Step three, take root, means square root. Square root. Now, voltage uh, voltage ms value, mean square value of voltage is V naught square over 2, and VRMS value, root mean square value, equals to square root of V naught square over 2. I hope you can see square root can cancel with square, but it will only happen for the numerator. In denominator, there is no square. So we get VRMS equals to V naught over under root 2. So this is a very important formula. Similarly, current MS and current RMS values. Current MS value will be I naught square over 2, and current RMS value will be I naught over under root 2. So this is important.
So when do we use this upper and lower formula? At what time?
Like if we need to find average current, and we are dealing with alternating current, because average of equal positive and negative data is always 0. Okay, so these two formulas are very important. Peak power equals to P naught. P naught equals to V naught into I naught. What will be PRMS? It will be VRMS into IRMS, which will be V naught over under root 2 multiplied by I naught over under root 2. So it will become PRMS power R equals to V naught I naught over 2. Remember, there is no square root in power RMS value, because when under root 2 multiplies with under root 2, we get 2. And from this one, we can also see power RMS equals to power naught over 2. Again, there is no square root, because V naught I naught is power maximum power P naught. So divide by 2 will be PRMS. Root means square value of power. Now, what are the factors that can increase the EMF produced over here? Now, how many different ways we can increase the EMF produced?
Changing voltage.
Good. No, voltage is EMF. How can we increase or decrease EMF? EMF induced depends on strength of magnetic flux density, speed of coil, angle of coil with respect to magnetic flux, number of turns in the coil. All these factors that can, they are the one that can change the EMF induced, the value of EMF induced. Number one, strength of magnetic flux density. Number two, angle at which the angle at which the coil is with respect to the magnetic field, number of turns in the magnetic field, and speed of the coil. Now, if you use speed method, there is a problem. If you use speed method, there is a problem that by increasing speed, we will be completing revolutions in less time. That means that will change the time period. And if time period is changed, there is a chance that there will be change in frequency. And there is a chance that frequency can be a problem. The different electronic appliances, they cannot work in specific frequencies. And sometimes they only work with specific frequencies. In those cases, changing frequency can be a problem. So we need a consistent frequency. The household electricity that you have at your home, it has a fixed frequency of 50 hertz. Okay. Now, if we increase speed, there is a problem. If we move the coil faster, there's no doubt more EMF will be produced, but the problem will be that the coil will be completing revolutions too quickly. That will decrease the time period and can increase, or will increase, not can increase, will increase the frequency. So here we go. Frequency of alternating one over time period. F equals to 1 over C. And omega equals to 2 pi F. This will be coming back again, omega. And omega is also equals to theta over T. And theta equals to omega T. Now,
Sir,
yep.
before you start the new thing, could you go back so I can take pictures of the last 2 pages?
Now, function alternating current. I equals to I naught sine omega T. And V will be V naught sine omega T, where omega equals to 2 pi F. So I equals to I naught sine 2 pi F T, and V will be V naught sine 2 pi F T. Now, let me make a key for you. I naught is peak current. I is current at any time T. V is voltage at any time P. V naught is peak voltage. F is frequency. T is time duration, or time on x-axis, or time on time axis. Okay. Sometimes instead of sine, we can use cos. There is no difference. They both can go for one. Like if I will be I naught cos 2 pi ft, then V will also be V naught cos 2 pi ft. You'll get the same answers for both. Now, function of alternating current. Okay. Rectification. This is a phenomena of converting alternating current to direct current. Okay. So we will resume from this at this point tomorrow.
एक मिनट सर, इसका भी स्क्रीनशॉट ले लेना प्लीज, थैंक यू।
Take it now.
Yes, sir. Assalamu alaikum.
Sir, could you